Instant query autocomplete with tries and prefix search. You will learn to build a fast prefix index, produce ranked completions by popularity, and validate results using a try walk. By the end, you can suggest the top suggestions for a typed prefix, filter noisy queries, and control how many results the system returns. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Query autocomplete matters because it minimizes latency for users. A good prefix index gives near constant time lookups, so keystrokes feel instant. The trade-off is memory and index build time, since storing lists per prefix duplicates strings. In practice, this approach serves thousands to hundreds of thousands of unique queries comfortably in memory and yields millisecond lookups for common prefixes. It shines on exact prefix matching, and it is not built for fuzzy or semantic matches without extra tooling. We will build a tiny pipeline that creates a prefix map, then a try, then scores by frequency, then filters by a popularity cutoff, and finally validates prefixes with a try before returning top K suggestions. This snippet builds a simple prefix index and retrieves completions for the prefix ka. It creates a small toy list of words and an empty dictionary named pref for prefix lookup. A nested loop walks each word and then each growing prefix, and appends the full word under that prefix key. So every prefix points to all words that start with it. The pattern uses setDefault to initialize a list the first time a prefix appears, keeping the code compact. A lookup on the pref entry for the prefix CA returns all matching words using constant time hash access, and the printed output confirms the grouped suggestions. Next, we build the try skeleton. This snippet builds a minimal try structure and prints the top-level branches. It starts from an empty dictionary named try and iterates through the same words. For every character, setDefault creates or follows a nested dictionary, forming a branch corresponding to the path of that word. When a full word ends, the code records a dollar marker to indicate a terminal node, so exact matches can be detected later. Printing the sorted root keys shows the first letters available, which mirror the dataset's initial characters. The output confirms the nested dictionaries form a traversable structure for prefix walks. Now we introduce popularity ranking for suggestions. This snippet ranks suggestions for the prefix CA using a frequency signal and returns the top two choices. A frequency dictionary named Freq records how often each query is selected, providing a simple popularity metric. The code pulls candidates for the prefix from the prefix index in constant time, then sorts them by descending frequency using an alphabetical tie-break to keep results deterministic. Slicing the sorted list to 2 items yields a compact shortlist that prioritizes common queries. The printed pair shows which candidates the system would promote for this prefix under the current frequencies. Next, we add noise reduction via a minimum popularity threshold. This snippet applies a frequency threshold before ranking to filter out rare queries. A variable named THR sets the minimum popularity a suggestion must have to be considered. A list comprehension filters candidates from the prefix index, keeping only words whose recorded counts meet or exceed 3. The code then sorts the filtered candidates by the same frequency first rule to preserve relevance and deterministic ordering. Raising threshold reduces noise and yields fewer but higher confidence suggestions, while lowering threshold increases coverage at the cost of potential low-quality items. The final output displays the cleaned and ranked set for the current prefix. Finally, we validate the prefix with the try and return top K results. This snippet walks down the try to validate the requested prefix, and then returns the top K ranked candidates. The code uses a variable t to traverse the nested try dictionaries using each character from the prefix p, short-circuiting and stopping early if any branch is missing. When traversal succeeds, the code computes the k highest frequency candidates from the prefix index, keeping deterministic ties with alphabetical order. If traversal fails, the result becomes an empty list, so no work is wasted on non-existent prefixes. Increasing K shows more suggestions and may add slight latency, while reducing K makes responses faster and tighter. Recap: it is a prefix map plus a trie for quick autocomplete. Useful when you need millisecond keystroke responses. And a key caveat is increased memory use for large vocabularies. Use this when exact prefix matching and speed matter, and avoid it when you need fuzzy or semantic suggestions without extra components. Next step, scale this pipeline to a larger corpus and add timing and accuracy checks so you can measure latency and suggestion quality under real load. If practical search tips help you, subscribe and watch the IR videos.